It's a great pleasure to have here Professor Weiner, very distinguished speaker for our fourth colloquium in this semester. And it's really a great honor and pleasure for me personally to introduce Andy, since I know him for quite a while. So Andy is a distinguished professor at Electrical and Computer Engineering at Purdue University, not very far from here, obviously, and he's not a novice on the campus. But what he'll talk about today is work that probably was not covered on his relatively frequent visits here. So Andy Weiner is very distinguished really in the field and very well known for his femtosecond pulse shaping work and for ultrafast signal processing. He is an elected member of National Academy of Engineering and National Academy of Inventors. He got all highest prizes from many societies, including Optical Society of America, Woods Prize, and Quantum Electronics Award from IEEE Photonics Society. He is the author of the textbook and many other accomplishments along his long and very distinguished career. So it's really a pleasure to have Andy here, and as a token of our appreciation of him accepting this invitation, I want to give him this memorabilia plaque over here.
Wonderful. Thank you.
So,
good.
Yeah.
Good. Let's put this. Good. Is this on? Yuri, thank you very much for the invitation and the introduction and for the beautiful flag. I actually thought it was going to be an Illinois t-shirt, which I would also proudly wear, but no, there's no issues with this fitting me, so thank you very much. So I'll be talking this afternoon. My title, Photonic Signal Processing, Ultrafast, Broadband, and Quantum. This picture is supposed to illustrate a waveform. As electrical engineers, particularly those of us who still remember analog electrical engineering, we like signals, variations of a signal with time. I've been very interested in manipulating signals in an analog way on originally a time scale that was ultra fast, picosecond and femtosecond time scale. So I'll tell you some about how that is done, and then extending into different areas. And so signals that may be very broadband, but not necessarily ultra fast, and even some in recent years getting involved in quantum signals that are maybe very broadband, but not ultra fast and not even deterministic. So just because this work grew out of ultrafast optics, I thought I'd give just a very brief introduction. First of all, what do we mean by ultrafast optics? So pulses of light on the picosecond, femtosecond, and faster time scale. So really starting here at nanoseconds, this is easily accessible by electronics. It's fast, but not really ultrafast. When you get down to 1 picosecond or 10 to the minus 12 seconds, it's getting pretty difficult to access this sort of time scale directly with most electronics, and going much deeper into the femtosecond time scale, 10 to the minus 15 seconds, essentially you can't do it. When you get down, to give you an idea of time scales, one thing to think about is if you have a pulse of something traveling at the speed of light, so a pulse of light of a duration 1 nanosecond, and you take a snapshot, it's about 1 foot long. As you get down to a picosecond, it's about 0.3 of a millimeter, so it's sort of the thickness of a business card. And when we get down to a femtosecond, it's 0.3 of a micron, so this is really around the wavelength of light. Actually, it's around 1 wavelength being ultraviolet at 300 nanometers. And so it essentially sets the limit of the shortest pulse you can get using visible light is on the order of a femtosecond, really a few femtoseconds. For some time now, people have been using femtosecond pulses in extremely nonlinear optical processes to generate hundreds or even thousands of harmonics into the X-ray regime. And so there people are pushing to even faster signals measured in attoseconds. Here we'll talk about picoseconds and femtoseconds, which are regimes you can access using visible light. Now, there are a lot of applications, but I think three of the key qualities of ultrafast light that have made an impact are illustrated by three Nobel Prizes that directly involve ultrafast optical light. Starting from my side, back almost 20 years ago, there was a Nobel Prize in chemistry to Ahmed Zewail for something he called femtochemistry. And basically, he's using femtosecond light pulses as ultrafast strobes to, in some sense, take time action, not really photographs, but measurements of ultrafast chemical processes. So the time scales for nuclei to move and vibrate can be tens of femtoseconds up to hundreds of femtoseconds. And he was able to perform the first experiments that actually made sort of time resolve the initial interesting emotions involved in light-initiated photochemical reactions, really photodissociation reactions. So sort of kind of using ultrafast time resolution for measuring ultrafast events. In the middle, back in 2005, there was a physics Nobel Prize awarded in part for something called frequency combs. And the idea is that having very short pulses of light, they have very broad bandwidth, as shown in sort of this picture. The shortest pulses of light can have bandwidths that span the visible spectrum.
You have one?
I do, but this might be a better one. Does it work?
That's what I'm trying to find out.
You know, my days in the dark laser lab are long behind me, so I need help turning on the laser. Oh, that one. This is much better. Okay, this one you can see. This is useful. Thank you. So you can have spectra that span the visible, yet if one looks at high enough time resolution, what we call mode-locked lasers, sources of femtosecond pulses, generate periodic pulses of light, typically at a few nanoseconds separation. And so if you have a periodic signal, there's a discrete Fourier spectrum. And if you look finely enough, you find that there's evenly spaced frequencies of light. There can be hundreds of thousands of these in the shortest pulses. And with some of the techniques that were really discovered leading to this Nobel, one can actually measure them with very precise resolution and stabilize them. So you end up having a frequency ruler that spans the visible, leading to frequency measurements with resolutions of 1 part in 10 to the minus 19, and becomes a central thing for reading out things like optical clocks, which are revolutionizing the ability to measure time. So bandwidth and frequency resolution somehow are also married in femtosecond pulses. Most recently, within the last 2 weeks, we had a Nobel Prize in physics that was half of which was given for a technique called chirp pulse amplification to George Moreau and Donna Strickland. And this was looking at the intensity of the short pulses. So the idea is if you have a laser that can put out typically constrained and sort of the average power it can emit, then the way you can grow peak intensity is to make a shorter and shorter pulse where the energy is piled up to give you more and more peak powers. One of the problems in doing that is you start to damage materials. And so in chirp pulse amplification, the innovation was instead of amplifying the short pulse directly, to first stretch it in a controllable way so the frequencies are spread out, amplify. Now the peak power could be as much as 10 orders of magnitude smaller if you stretch enough, and then recompress and realize intensities you couldn't have otherwise. So these days people can focus light to reach intensities of 10 to the 20-something watts per square centimeter to really explore physical conditions that are otherwise completely unattainable, and sort of a new light matter regime of interactions is really what led to this Nobel. So I won't be talking about chirp pulse amplification, but you will see some hardware that is related to the hardware using for stretching and recompressing short pulses. I'll talk a lot about pulse compression. So it'll be a little bit of a tie-in there. Now, all of these techniques are somehow related to looking at ultrafast light as delta functions, or extremely short impulses of light. My interests have gone in somewhat of a different direction, and I like to make very broadband, highly structured light with fast time content, but to make complicated, engineerable, user-specified waveforms. So we'll call that pulse shaping or optical arbitrary waveform generation. And so I'll tell you a little bit about that technology and how it touches on in my laboratory, several different areas that are kind of not traditional regimes for ultrafast optics. So for example, in fiber optics, there's interest in transmitting very broad bandwidth optical signals. I'll tell you a little bit about how our ultrafast techniques can interact in interesting ways with fiber optics. There's some interesting things one can do with hybrid photonic RF or wireless systems. So that's why I have an antenna there. And I'll talk a little bit about using shaped ultrafast light for making interesting very broadband RF signals and looking at some aspects of wireless propagation. In the last two, we've also for several years been interested in somehow the confluence of actually making ultra-short pulses from integrated photonic devices, which can work either in nonlinear optical regimes or at lower intensities, generating interesting states of quantum light and quantum entanglement. So I'll touch on each of these topics, at least provided I speed up a bit. So the introduction, I'll start off talking a little bit about how we learned how to make almost arbitrarily shaped ultrafast pulse waveforms. I'll give you a few examples and touch base on a little bit of interaction with fiber optics. And I'll talk about some recent work in our lab, some of which may date back 15 years, but not 30 years, but all of which is active in one way or another still currently in our activities. So that will include sort of the interaction of photonics with broadband wireless, a little bit about frequency combs from these integrated micro devices, and a little bit about what for us is a relatively new area, venturing into quantum optics and entangled photons. So the arbitrary waveform generation or pulse shaping we'll do is all based on sort of simple Fourier transform, Fourier series concepts. Since this is probably mostly an EE audience, you're familiar with this, but so very quickly is the idea that we can decompose signals here as a function of time into a superposition of frequencies. For a non-technical audience, sort of musical tunes, but from a technical point of view, we think of adding up sinusoids here. If we have 1, 2, or 5 frequencies, and if they're in phase, we can add up more and more to make pulse-like signals. I like this figure here because you can see these instants of time where the 5 sinusoids all have peaks in the same place, so those are in phase. They contribute to make short pulses. So to make a very short pulse out of a laser or any signal, for example, you want a bunch of frequencies that all add up in phase. We'll be controlling phase quite a bit in examples in this talk. So to look at phase a little bit, one illustration is this one here, where we simply have 2 frequencies at harmonic and its second harmonic, and simply vary the phase or the relative temporal alignment of one signal with respect to the next. And as you can see and probably expect, that changes the waveform from something that's maximally pulse-like to minimally pulse-like. And so just sort of an illustration that phase is very important. And again, phase as a function of frequency is going to be kind of the main theme that keeps showing up in all the different examples in this talk. A more sophisticated example, one familiar probably in most undergraduate classes on signals and systems, is Fourier synthesis of a square pulse, as shown in this animation. And so if we add up a series, as shown in this animation, it's, at some point it starts, and adds up a first harmonic, a second harmonic, a third harmonic, one after another, up to 31 harmonics. And as we do that, we see that the sum of those becomes more and more square pulse-like. You can see the harmonics themselves have different amplitudes, and they reverse phases, signs, so they have pi phase shifts that you have to worry about. And so anyway, this is an example of the sort of thing we became interested in, or succeeded in doing with femtosecond pulses. Okay, so flipping now to femtosecond optics, how does this work? So the assumption is, in our original work, is that one starts with a short pulse, one of these delta function-like pulses, a picosecond or hundreds of femtoseconds long, maybe shorter, coming from a mode-locked laser. So I won't talk about how the lasers do this, but lasers are commonly thought to be monochromatic devices. That's one of the ideal ways that a laser works. Really, it's understood now that the other ideal way that a laser works is many frequencies being, instead of single frequency and constant in time, is essentially many frequencies and sort of delta functions approximately in time. And so lasers now can do this in many different forms. And so a short optical pulse comes in. It's got a lot of frequency content, but it's too fast to directly use electronically controlled modulation to reshape. So an idea that I was involved in developing to make new waveforms involves an apparatus like this. A diffraction grating is a component that simply takes input light and causes the output diffracted light to go off in different angles depending on frequency, and sort of a nice uniform gradient of angle with frequency. Okay? And so if you come in with a short pulse and hit a grating, different frequencies, only which two are illustrated here, come off in different angles. With a focusing element such as a lens or curved mirror, those can be focused to small spots that are now spread out. So if this is all you do, this is the front end of a spectrometer, which is kind of an instrument that's been known for hundreds of years. An innovation involved in pulse shaping is, instead of measuring the light here, is to put a spatially patterned object. So some object that will allow you to control on a spatial by spatial basis either the amplitude of the transmitted light, the phase of the transmitted light, or perhaps both. Okay? And because frequency and space are mapped together, that spatial pattern becomes a complex pattern on the optical frequency spectrum, so it allows you to control your Fourier spectrum. With another grating and lens, you put all the light back together, all the frequencies back together. You get a new waveform. Here's two examples, where the new waveform in time is the inverse Fourier transform of the spatial pattern transferred from the mask or modulator array onto the spectrum. So two early examples that I still like are taking a short pulse, reshaping it into what you can think of as a femtosecond data sequence. 4 pulses on, 1 off, 4 pulses on, spread by a few hundred femtoseconds each. Or scrambling the phases of the noise so they don't add up to short pulses into pseudo-noise waveforms that might be used in some spread spectrum concepts. These are noise-like, but can be put back together because everything's deterministic. By the way, these setups of pairs of grating pairs are the elements that are used in sort of stretching and compressing light in things like short pulse amplification. This idea here of putting in modulator arrays to reshape the light is sort of taking those kind of physical setups in a different direction. So a couple of pictures. This is a picture of what this might look like in a laboratory. These days, most of our light is coming in and out of optical fibers in the 1.5 micron band. It's invisible, so this is colorized. But we had a diffraction grating. 2 representative frequencies of light come through a lens. This is a liquid crystal spatial light modulator that has a bunch of reconfigurable pixels, sort of like a liquid crystal display. We can control phase and amplitude individually, probably in this one at 128 different locations. It uses a mirror to actually go to fold this and go back through and into the optical fiber. This is a commercial implementation. Boxes like this have been available probably for 7 or 8 years and are closely related to developments in light wave communications with devices called wavelength selective switches that can do independent switching of light at different wavelengths and different fibers that are really built off of engineering setups like this for more advanced functionality. Okay, so there's a lot of applications ranging from sort of ultra-fast science, which mostly I won't be talking about here, to things that are more kind of information-related, fiber communications, radio frequency photonics, et cetera. So some examples. First example is sort of, I'd say, motivated by this classic experiment from 200 years ago from Thomas Young, his famous 1 or 2 slit diffraction experiments. And focusing on the 2-slit one, here he put quasi-monochromatic light through an opaque screen with 2 slits, observed in the far field this sort of modulated pattern with this fast modulation. So what happens in this type of diffraction is 2 spatial frequencies in the far field interfere with each other. Propagation of light in the far field does a spatial Fourier transform. And in some sense, this will come back when this was one of the early evidences for the partial wave nature of light. Interference phenomena. We'll see a lot of this, particularly in the end when we come back to sort of entangled photons, the ability to interfere, let's say, certain degrees of freedom of different photons. This interference is key to showing the entanglement. So somehow these ideas will come back. But first, what I want to show is one of the early pulse shaping experiments It's essentially a time domain analog of Young's two-slit experiment. So the idea is we have a broad spectrum that might look something like that in frequency. A mask was put in to block all the frequencies except for two that are isolated. So those should beat now in time to give a modulated ultrafast pattern, which you can see here is the red one, several picoseconds long, beating at a few terahertz. Another companion experiment was done with the same type of mask, but another element to give a pi phase shift, sort of flip the sign of the electric field in one of the frequencies. And now these still have to interfere, but they get shifted, and you can see actually get the nice temporal shift. So a very simple example, a simple element in the Fourier domain, already generating fairly highly structured light in the time domain on an ultrafast time scale. Also the square pulse. So this is the one that I foreshadowed. So to make a square pulse, we need to take the input spectrum and carve it into a sine x over x function with a series of side lobes and phase reversals for some of those side lobes. And in those days, we weren't using yet liquid crystal displays that could be reconfigured, but using microfabrication to make gold on glass masks. Wherever it's light, there's no gold, and so the patterning is done to, on average, give you a strong central lobe and a series of side lobes. If we use another mask with more side lobes than shown here, we can carve a broad spectrum into a peak with, I think it's plus or 15 side lobes on either side, something like that, about 3 to 30 dB dynamic range, and come pretty close to the target. If you add to this some phase control masks, which aren't shown, you can reshape input light with a sort of 100 femtosecond input scale, like the rise time here, into a square pulse with fast rise and fall times, a few picoseconds long, that respectively comes close to what was expected theoretically. So again, showing you can start to do some complex engineerable manipulations of ultrafast light. So I want to talk more about the phase, and this will get us into something we call dispersion, or chromatic dispersion. What it means is in most materials, including optical fibers, including very thin pieces of glass, and ultrafast optics at the few femtosecond scale, if you go through a millimeter of glass, you see very clearly that different frequencies of light propagate at different speeds, and the light spreads out, the frequencies spread out. In fiber optics, this might be more meters to tens of kilometers, depending on the time scale of your light. But the idea is that you have a frequency-dependent delay that spreads out your pulse more and more, gives you what we call a chirp with different frequencies versus time no longer lined up on each other. And if we look from the phase point of view, the phase versus frequency, the lowest order signature, this is a quadratic. So a quadratic spectral phase, this is showing increasing dramatics, gives you a linear variation of delay with frequency. And with larger and larger quadratic phase, larger and larger dispersion effects. So again, this is interesting from few femtosecond ultrafast optics to sort of fiber optics. We're going to talk a little bit in the concept from the perspective of fiber optics, which is an area that we've done a fair amount of work. So a picture of an optical waveguide. As probably you know, fiber optics are used essentially for any kind of real distance conveyance of almost all data, information, internet, et cetera, et cetera. And there's two principal reasons we do this rather than using electrical cables. Probably the first of these is electrical cables are lossy at interesting frequencies of gigahertz, numbers like hundreds of dB per kilometer, so after a kilometer your signal is completely gone. Optical fibers can have losses down to 0.18, something like that, dB per kilometer, so you can go 50 kilometers and still maintain at least 10% of your intensity. So the loss is just dramatically different at high frequencies. And second, and interesting for us, is there's a significant bandwidth over which you have low loss. So you can define it in different ways, but I'd like to say nominally the lowest loss region is around 10 terahertz wide. Conventionally in fiber optics, that's split up into frequency or wavelength bands that may be spaced by 50 or 100 gigahertz, each representing different data channels. But you can also think about, and we did, as this is a medium that might be able to support transmission of pulses down to about 100 femtoseconds, one over the bandwidth. And so I'll talk a little bit just about sending short pulses over fibers. Now the idea here is that if you send a short pulse over a fiber, it spreads out. That's what we mean by dispersion. This became of interest within the fiber optic communities in the late 1990s when the commercial systems were first reaching 10 gigabits per second. They're much more advanced than that now. But the pulses were getting short enough with enough frequency content that they began to spread out undesirably in sort of 50-kilometer distances that were limiting the data rates of the systems. So industry said, well, let's develop special fibers that became known as dispersion compensating fibers, where the derivative of a delay or velocity with frequency was opposite in the dispersion compensating fibers compared to conventional ones. So with appropriate length ratios that you concatenated, you could have pulses that would spread out in the first fiber and come back together in the second fiber. Okay? And now eventually, if you go with more and more bandwidth or shorter and shorter pulses, you'll find that the match isn't perfect. And then we asked, you know, how much can we use our pulse shaping technique to fine tune this and extend to shorter durations the pulses you could send without distortion. Okay, and so how do the pulse shapers come in? Well, this is close to the only math in this talk. But if we think about dispersion from a technical point of view, we can understand it if we play with Fourier transforms just a tiny bit, as the frequency-dependent delay, that's what tau of omega is related to the derivative of the frequency-dependent phase with frequency. So just d psi d omega. Okay, so if we want to impart or compensate a frequency-dependent delay, you know, the opposite of whatever is causing this distortion, we just need to construct the right frequency-dependent phase that has the right derivative. So the pulse shaper is an instrument that allows us to program in spectral phase, and so that's what we set about doing. So we call this a programmable spectral phase equalizer that fixes the little bit of distortion that's left. This idea is used, you know, in other fields, particularly in few short pulses, compression and short pulse amplifiers and so forth. So in fiber optics, I'll show you two examples. The first of these was about half a picosecond pulses with about 3 kilometers of this concatenated dispersion compensated length. In the days we did this, these were pre-commercial dispersion compensating fibers. We were able to get one from a friend at Bell Labs, and my students sort of unwound it, made measurements, cut it laboriously, sort of meter by meter to get the right length. But so eventually what they're able to do is send in a half a picosecond pulse. This isn't shown, but in the first fiber it spreads several hundred times. If you get the fiber length right, you put it almost back together, you know, 490 femtoseconds to 770, but with a little bit of remaining distortion. Okay, what the distortion comes from is because there's higher order derivative terms in the spectral phase that aren't matched in the two fibers, and so there's a cubic variation of phase versus frequency that causes this. So we figured that out. We were able to program now a cubic phase versus frequency. This should say phase in units of pi. That's exactly sort of equal and opposite to what's causing distortion. Your pulse comes back essentially within measurement limits without distortion. So this is not very far in fiber, but at the time this was kind of the best combination of short pulses and long fibers. We did this a couple times. A few years later, these dispersion compensating fibers were commercialized. You could buy boxes where the fiber length was matched to that of a 25 or 50 kilometer single mode fiber. So now you just sort of plug and play. We did it again. So came in at half a picosecond input pulse again. Now with a longer fiber, after single mode fiber, we spread by 4 orders of magnitude to 5 nanoseconds. Plug in the dispersion compensating fiber. We come back to this black curve, which looks pretty awful, but it's gone from 5 nanoseconds to 14 picoseconds. So it's like 99.7% fixed. Again, we've got some unmatched quadratic phase. The lengths weren't quite right. They were good enough for industry, but not enough for femtosecond pulses. So we program in a quadratic term. Now we get this blue thing, which is almost fixed, but has an asymmetric tail. That's the cubic term. Now we independently overlay that. We back the red curve, which is essentially undistorted again. What's maybe interesting here is look at the phase profile. So the actual phase profile is this thing here. Okay, our devices can make a little bit over 2 pi, but 2 pi is, you know, all the phases matter only modulo 2 pi. So you make this very complex thing. If you unwrap it, this is really, you can see a combination of quadratic and cubic, so you can control it well enough to fix distortions like this. Okay, so that's an introduction to pulse shaping. Let me skip forward just a little bit based on my time derivative here to a little bit about the RF work. So what we're going to talk about here is combining pulse shaping with making broadband RF waveforms and a little bit about wireless propagation. So the background here is if you want to, there are electronic instruments that you can dial up and make arbitrary waveforms. And like most electronics, they're getting faster and faster, but optics still has more bandwidth. And so the technique we're going to look at here is taking our femtosecond pulse, we're going to shape them. I call it a programmable arbitrary spectral filter. Here we're not going to use phase, we're going to just shape the spectrum. So this is a spectrum that fills up the light wave C-band. That's about 5 terahertz of bandwidth, or about 40 nanometers. We're going to reshape it into this sort of frequency modulated looking thing. And now we're going to send it through a fiber. Now we're going to use the dispersion on purpose, where it stretches out the different frequencies. So in a certain approximation, each of these different frequencies maps to an instant in time. So we can now make this pulse stretch to nanoseconds with this kind of complex frequency hopping structure. At the time we did this is really kind of when we entered this field of broadband RF photonics. This was beyond what the best electronic instruments could do. Now the best electronic instruments are better and can do tens of gigahertz. We've still got one I think is beyond the electronic capabilities. So if we revisit this concept recently and do the same thing, not quite the same thing. Here this was easy. Here we have to learn some things about the details of how to do the right waveform synthesis. But without getting into the details, in the end we can use the same setup, program it a little bit more intelligently, to make signals like this. This is a chirp signal, or frequency modulation signal, that goes from a high frequency at 45 gigahertz down to a low frequency around 4 gigahertz. That's 4 point something octaves. That's usually hard for RF systems to deal with. But you simply stretch the light out, hit a fast photodetector, and you realize a waveform. And if you look at little parts of it, it's very close to the target. So this is, again, somehow a very high precision waveform engineering tool that now can be used to make broadband RF signals in a range where they're still kind of difficult to make by conventional means. So there's a number of things we've been interested in this, but let me just illustrate a few things. One of the even higher frequencies, what if you want to go up to what's the W band? That's 75 to 110 gigahertz. This is, I think, the highest frequency. You can still get any components like RF amplifiers. And so we're working here with a colleague in Taiwan who does sort of advanced research of photomixers or photodetectors that can work at these frequencies. So same technique I showed you before. It looks sexier now because there's these little chips. This is an optical microlens. You come in with the fiber and bring your short-shaped pulses in. That couples into a waveguide, some of which you can probably see here. You can see some waveguides. You can see some horn antennas, which are about so big for this kind of 100 gigahertz frequency band. And so we can realize these burst RF signals. It's kind of hard to see here, but this is a 35 gigahertz bandwidth chirp centered at 92 gigahertz. This is a time frequency representation. Again, sort of making this kind of controllable bandwidth signal at these frequencies. I don't think there are any other technology alternatives right now. So what are these good for? One thing is ranging. People like to do ranging with wireless or RF signals, radar. And it turns out in radar, the range resolution you can get, or the time resolution, doesn't depend on the length of the waveform. It depends on the bandwidth of the waveform. If you have the bandwidth and can measure it, you can post-process it, either in hardware or in software, and to get compression. And this sort of, by the way, the chirp pulse amplification thing in optics was influenced by the first chirp radar experiments that came around during World War II. So chirp radar is very known. So we have chirp pulses. Here you do it because you want to keep the intensity low so it doesn't saturate your transmitter, but you can get more energy in a long pulse, and you compress at the end. So what we did is some ranging experiments where one of these is a transmitter antenna. One of them measures return signals from various metal objects we put within the largest lab I have at my disposal. And if you do that, you receive the waveforms, do the right post-processing compression, you can get signals like this, where we see this first return is from the sphere, which kind of spreads the return out. These kind of metal plates give you a more direct return, so they're higher amplitude. So you can see many return signals. And if you look at one of these, two of these plates, we can move at millimeter scale relative to each other, and we can discern different return peaks at few millimeter scale. So as far as we know, at least in published literature, this is the best range resolution you can get at this frequency. To get this much bandwidth with electronic generators, you have to go up to like 600 gigahertz, which is quite challenging in its own. So we think, we're doing some more work in trying to do range-resolved imaging with this. But let me talk a little bit instead about shaping wireless. So let's go back to sort of dispersion or distortion of waveforms and fixing that. So what we're going to do here is send in a short pulse into a commercial antenna. I think this is a 2 to 18 gigahertz type of bandwidth. It's easy to get commercial broadband antennas. But not all of them, but many interesting antennas have what's like dispersion in them. They have a delay spread in terms of emitting different frequencies at different delays. And so we have this antenna link that's like 2 meters apart, just two antennas staring at each other. And what happens is we're going to come in with a short pulse. We've done shorter, but this will kind of prove the point, 200 picoseconds. We excite this link. We get a lot of bandwidth out, but you can see the chirp. High frequencies coming out, then low frequencies. Spreads 10 times. Okay? And so what you can do then is you can reverse this. Here the technique is actually how you drive this antenna. So you'll drive it with a precompensated waveform that's essentially flipped in time. More precisely, we have the spectral phase conjugate. We just sort of switch all the spectral phases responsible for this signal. So this is kind of a version of a predistorted waveform that's kind of flipped in the high frequency, low frequency sense. We can make it in our photonic waveform generator. It comes out and now it recompresses from the full system point of view. Okay, so this was kind of a fairly novel demonstration. And after a number of experiments like that, you can say, okay, what can I do that's harder? Okay, and what's harder is real wireless. Okay, and so real wireless, mostly you don't have two antennas that are staring at each other, but in indoor wireless, certainly your signals are bouncing off walls, they're going through walls, they're bouncing off the floor, they're going through all of you, and you get something called a multipath, meaning that if you were to send in a short impulse, you get a bunch of sort of random-looking delayed echoes. Okay, different amplitudes, different phases, and these are some real data. If you move the receiving antenna, you get something that looks statistically the same, but all the details are decorrelated and different. And so we asked, can we do something about this? And can we learn how to measure what can be very complicated waveforms and then make flipped versions that recompress in this multipath scattering environment? So we're going to do that, and if you do that, what should happen is you make a waveform that, say, matches this one. You get a pulse here, but it doesn't match this other antenna, which has a decorrelated signal, and it should sort of stay messed up, if you will. And so kind of the idea is here, possibly ideas like this could be interesting for some sort of built-in covertness or privacy and broadcasting your wireless signals. So let's just see a couple examples. This is an example that's indeed done with kind of optical-based RF waveform generators I described. So we have a receiving antenna that we can move to two locations. This is, I think, 2 rooms away from our transmitting antenna, probably about 10 meters. But a sort of 100 picosecond-ish RF pulse comes in, and you can see it spreads out to tens of nanoseconds. And the two antenna positions that are 10 or 15 centimeters from each other, you have a very different response. So now we can make a waveform that compensates this channel. Here we get a peak, and the other antenna we don't get a peak. Now we reprogram our waveform based on the second measure, channel response that we measure. Now we get a peak over here. Okay? You can take this a little bit farther. It turns out that optics has more bandwidth, but the electronics has more memory and can make longer, more complicated waveforms, which could be useful here. So we ported this idea to sort of some lower bandwidth, but still pretty interesting electronic waveform generators we had access to. Again, here's kind of the experimental transmitter receiver that can move 2 rooms away. So here you can see our even more complex channel response from transmitter to receiver 1 or 2 different channel responses. By programming the transmit waveform, we can peak it up at either receiver with quite a difference in the sort of signal to interference. Okay, so I've got sort of a note here telling me how far along I need to get through this, and I can see it's going to be hopeless. So at least I'll mention we can do this in multimode optical fibers, but I won't go into that. Let's talk a little bit about the frequency combs from microresonators. And so I already mentioned there was a Nobel Prize in frequency combs that came out of mode-locked lasers that are extremely broadband and some sophisticated techniques for what people call self-referencing for kind of measuring and stabilizing the absolute frequencies. I got interested in this a few years later. We didn't participate in making any of those spectacularly stabilized frequency combs, but viewing those as kind of a dramatic advance in precision broadband optical oscillators, we like to think of this pulse shaping as a precision kind of waveform engineering approach. And what about putting these together? Okay, and so there are some, these lines tend to be fairly close together in mode-locked lasers. There were some tricks, but we learned how to do pulse shaping in higher resolution where we could gain access to more closely spaced frequencies. With also some tricks on the source side, we were able to do experiments where we go in and put different phases on adjacent spectral lines. So even though I talked about Fourier series at the beginning, none of the data I've shown you before went into individual lines. They're all kind of a continuum of spectrum. Here we really access kind of a discrete optical spectrum. We put on this sort of different phase shape over 128 lines, and we can reshape some delta functions that were happening at 5 gigahertz at this frequency into complex waveforms with a lot of details. We can, again, hit the targets, very precisely. And the interesting thing here is that the waveforms are not isolated waveforms anymore. They fill up time and overlap from different starting pulses. And it turns out that this is one of the concepts that frequency combs bring in. They bring in the idea in the time domain that you have some predictable phase evolution from pulse to pulse. Phase meaning where are the peaks of the electric field with respect to the envelope. If you don't worry about high resolution frequencies in the time domain, you kind of don't worry about this at all. But in order to get stable waveforms, we need to have a stable phase evolution, and simply the fact we can make these measurements shows that we're using that attribute to the frequency combs. But so I want to go here into kind of the micro devices. And so there's some interest starting about 10 years ago, 11 years ago, on what about combs from very small devices. And so the first paper was from a group that's now in Switzerland, Tobias Kippenberg, who was doing work with very high quality factor optical microresonators. These are called Wissmann-Gally mode microresonators. And white light goes around this ring through total internal reflection. When they're properly fabricated, they can have quality factors in the many 10 to the 8th or 10 to the 9th type of region, which means they're very resonant. When you come in with light with the right frequency, it gets trapped inside and builds up to relatively, hugely enhanced intensities. And so under the right conditions, those enhanced conditions can lead to nonlinear optics, which sort of provides gain and generates new optical frequencies at all the different resonant positions of these cavities. So if you come in with a single strong pump line, you generate light at many of the different optical resonances. And the thought was that these could be, under the right conditions, equally spaced and act as a frequency comb. But now, instead of being a relatively large mode-locked lasers, it could be really tens or hundreds of microns type of chip scale structure. So this rapidly picked up. I'm showing several of the early devices. Some of these are chip scale waveguides in materials like silicon nitride. The first of those was at Alex Gaeta and Mikhail Lipson's group at Cornell. We were probably the next that jumped into this platform working in silicon nitride. You can see just a few nice pictures of the resonators that trap light that can be in either simple or kind of exotic shapes, as well as some structures we like to make to sort of mechanically support fibers that we use for coupling in and out. So most of the work at Purdue since the early days in this has been a close collaboration with a faculty colleague, Minghao Qi. So when I got interested, our first experiments were a few years after the first demonstration of frequency combs, which really had been looked at from a frequency domain perspective. And we're interested in what are the time domain signatures. And so a question we asked was something like this. What are the time domain properties? They act as ultra short, they act like mode-locked lasers. Meaning is the phase stable? Can you manipulate it? Which I have to confess, I assumed the phase was stable and could manipulate it, but we wanted to be the first to sort of show that. So and it turns out not to be so simple. But what we did is we come in this cartoon with single frequency light coupled into a waveguide. It couples at a resonant frequency into the ring. When the intensity builds up, you get new frequencies generated through nonlinear optics. So that's depicted as white. It's really not that broad band, but depicting more bandwidth. And then it comes out into, this is supposed to be a cartoon of a pulse shaper. We're going to try to manipulate the spectral phase and see if we can compress it into the shortest pulses provided by the generated bandwidth. Okay. And so this is kind of a more technical view of the same thing. What I'll point out are two things. In order to reshape the, we're going to try to reshape the short pulse. We're going to put it into an autocorrelator, basically a nonlinear optical device that is going to give us more intensity out if we have a short intense pulse. And so we're going to play with the different phases until we get the most intensity out. Then we're going to measure our pulses. And so two things. We're going to try to compress these pulses in the shortest possible. In the process, by learning what phases were needed to compress it, we'll learn what the waveform was inside the resonator. Okay. So what we found out is, a surprise to us, is sometimes they act like mode-locked lasers and sometimes they don't. So sometimes they have phase which is stable and can be manipulated, and sometimes, and most of the time, actually, they didn't. And so in these experiments, this is a case where it's sort of fully compressible. It's highly coherent, we would say. The output signal versus delay, or sort of time, is this blue signal, which doesn't look pulse-like at all. But by choosing proper phases, you can reshape it into something that's very pulse-like and very close to the best you could do, calculated based on the spectrum, assuming flat and stable phase. So this was sort of highly coherent, like a comb laser. But what often happened is you might even start with some modulation, that's the blue thing, but shape it the best you want. Maybe you can kind of reshape it a little bit, but you can never get this to come down to zero. And it should have come down to zero. Turns out in ultrafast optics, these measurements are a bit indirect. And really, the way you tell having a nice pulse apart from a kind of broadband noise with fast features is by the contrast ratio, how well does this come down to zero. So this is a signature of something that has high intensity substructure content and not really a short pulse. Some later experiments showed more extreme examples. This is a case where we can compress the pulses beautifully all the way down to zero. This is a case, the green one, where we can't do anything to them. And this sort of 1 to 2 contrast is the signature of something that's not a pulse, but just continuous sort of intensity noise. So this was a big surprise. Turns out we gained some insight into what's happening. And so when we had these coherent compressible pulses, we always found what that would happen is that we come in with a pump light at one frequency and looked at how the spectrum developed, it cascaded output. So we made sidebands at the first available resonances. They did nonlinear mixing. They split with each other. If you were to work that through, you'd find out there's kind of no choice but to reproduce precisely the initial frequency spacing. And then you get nice controllable phases. But what often happens in these devices, you get something like this, where you skip a resonance. This one shows you come to the, I think the third resonance. Can I see this? Yeah, the third resonance. Then at higher intensity, you fill in some of the missing resonances. Okay, it could be 3, and this data over here, where we have a fully developed spectrum, the initial lines are 27 resonances apart, and then they fill in a dense way. And it turns out when you kind of work this out, there's no physics that guarantees that your initial wide frequency spacing gets divided in an integral manner. Okay, the resonances, in fact, are not equally spaced. The same dispersion I talked about gives them small relative shifts. And so you actually generate a series of combs that are kind of not equally spaced and interpenetrating, and they beat in these awful noise-like ways. So this triggered quite a bit of work. People learned within a few years how to evolve out of these states into kind of coherent, more mode-locked states. I won't go into the details. It's now pretty well understood. An example from EPFL looks something like this. These broad spectra, strong pump line, but these frequency-resolved optical gating measurements show that you really have a single pulse per round trip with very short pulses developing. So it's kind of magic. Come in with a short pulse, this nonlinear microresonator, and it self-organizes into periodic pulses. Okay. For those optics people there, dispersion means something. If you have nonlinear optics, the sign of the dispersion, or whether red frequencies go faster or slower, is very important. The interactions are very different. It's originally felt that these could only develop with what's called anomalous dispersion, like solitons and optical fibers, for those who are familiar with it. We found in my group, and I have to admit kind of by accident, that it was actually possible to generate combs in normal dispersion devices through some more subtle formation mechanisms. But we can make stable mode-locked combs. If you do pulse shaping to compress these and learn what the phases are, these are not very good pulses. These are dark pulses. They're kind of a CW background with a frequency modulated intensity dips, but they're fully coherent. They can be compressed into short pulses. And it turns out these are more popular. These have more bandwidth, but only get about 0.5% conversion of pump to the comb. These are not very broadband, but still they can be 200 nanometers broad. They can have a lot of tens of terahertz bandwidth. but can be much more efficient and can be 30 to 40% conversion efficiency. And so I think there's more to learn about, how to better get more bandwidth here, get more efficiency here, and which one to choose for different applications. So I'm going to try to spend just about 5 minutes to talk a little bit about the quantum side. I've really kind of behind schedule. But so I see some people I know are much bigger experts here than I am in quantum optics, but many of you may not be. So let me give just sort of a brief introduction, first of all, to quantum entanglement, which is we're going to work on. And so we're all familiar with flipping coins. And so if we imagine we give two parties, Alice and Bob, which might be spatially separated, they're a coin and they both flip, their heads or tails are completely uncorrelated. And you can look at the probability of Alice getting certain events and Bob getting certain events. Okay. I have to say, by the way, this one I stole from one of my recent PhDs who graduated, and I thought he had a much more intuitive explanation than I ever had, so I borrowed it. Okay, but the interesting in the quantum mechanics is we talk about a wave function for what Alice and Bob does, and in some cases, depending on how the state is generated, we might find that really there's a superposition of both Alice and Bob having heads and Alice and Bob both having tails. And which it is not really determined until we make a measurement. Otherwise, it's an unknown superposition state. You kind of take this and do magnitude squared to get the real probabilities, which means the heads and the tails can have phases and interfere with each other and do lots of interesting things that are at the heart of many of the proposals that are out there for doing quantum computing and interesting secure things in quantum communication. So just briefly about we're going to work at a special type of entanglement called time frequency entangled photons or frequency band entangled photons that have the broad band character that our pulse shaping tools can do something useful to. So two general ways to make this. One is you send a single frequency of light through a nonlinear optical crystal that has the property that conventionally it will upconvert light to the second harmonic frequency. But worked in reverse, with some small probability, some of the photons coming in, the pump photons at 2 omega naught, will split their energy into two photons, which can both over some range have random frequencies, but the sum of the frequencies or energies has to preserve that original photon. So you get light, if you look at the two photons, what their frequencies are, any one of those has a broad range. In our experiments, 5 or 6 terahertz. Okay, but a fairly, can be an extremely tight correlation in the frequency of one versus the other. They have to conserve energy. Okay? And if you look from the time domain, these happen rarely. Okay, so they come out at random times, but when one photon, which you call the signal, comes out, the idler comes out with what can be a quite tight temporal correlation. So you have very tight broadband in frequency, random in timing, but very tight correlations in both frequency and time between the particles. Okay, so this is sort of a workhorse for several decades. Another approach that's coming online in the last few years, and one that we've been particularly interested in as well, is using these same microring resonators. Now you don't pump them as hard, so you don't generate the classical combs, but with some probability the photon coming in are really, in this case it's two photons come in, pool their energy and then split and divide it into signal and idler frequencies. Okay, this is sort of similar. The signal and idler can come out at different frequencies over some distribution, but they have to conserve energy. So you'll get a signal and idler on the right and the left that are exactly symmetrically displaced. And here a difference is it's discrete because the resonator supports discrete frequencies. Okay, so let's talk a little bit more about this. So just some examples of experimental results. These are with a smaller and a larger resonator. They look the same, but this one is larger by about 6 or 7 times. And what you do is you come in with strong pump light. If you look at the spectrum coming out, you get these sort of strong pump. It's already been knocked down by about 60 dB, 70 dB. But then that allows you to measure a series of signals and idlers. And the experiments you do now is you have to select signal and idler frequencies, which we can do by programming pulse shapers, and send them to 2 outputs, each of which goes to a single photon detector. And so you look for clicks on the 2 detectors coming at the same time. You call that a coincidence. And so you do this for different sets of frequencies. So the signal 2 and idler 2 should be correlated. You get a time correlation peak, coincidence. This is the third signal and idler, the third frequency either way. But if you look at the second of the signal and third of the idler, they're non-correlated, and your peak goes away. So you kind of make measurements for lots of signals and idlers. You get these diagonal characters. This is your frequency correlation. Okay, if you go to this other ring, these are spaced by like 380 gigahertz, photons here by 50. Here you get about 40 along the diagonal. So an interesting thing here is each photon can take on up to 40 frequencies. And so you can ask about, are these high dimensional units of quantum information, where instead of 1 bit per photon or qubit, could you have 5 or 6 here if you could figure out how to use this? This is an area we're interested in. So the last thought I want to give here, which will take 2 or 3 slides, is, well, what about entanglement? Okay? So entanglement, I said something about there's a phase, there has to be ability to interfere at different parts of the probability amplitude. And so looking at frequency correlations is part of the message, but says nothing about phase and actually doesn't prove that you have the entanglement that will be key for many of the things you really want to do in quantum information. So this is something that we, in parallel with one group in Canada, came up with in the last sort of 1.5-year time scale. And the idea is that our quantum information is encoded in different frequencies. You know, and in the experiments here, they're 50 gigahertz apart. It's hard to mix frequencies 50 gigahertz apart. They give you a fast sinusoid. It's much too fast to resolve in single photon detectors, so you've got a problem. So what we did is essentially used a PM as a phase modulator. This is a telecom device that you drive with RF, say 10 or 25 gigahertz. It puts a phase on the light that varies in time in the same way. And so we know from communications, driving things with sinusoids gives you frequency sidebands. So what we're going to do is start with, if these are our original frequency lines, when we drive with a phase modulator, tuned to half the spacing of the frequencies, we're going to generate new sidebands at all these green positions. And many of those will have several parent frequencies. This picture is showing examples of either 2, or if we drive a little harder, make bigger sidebands. Many lines contribute. Okay? So now if we filter out with another pulse shaper and grab a particular sideband pair and send to different detectors, we can look for coincidences, and there should be a superposition. And the way we test the superposition is going back to the first pulse shaper. We also put different phases on the lines, and so we're changing what we call the biphoton phase and looking for the coincidence counts to sort of oscillate versus the phase we apply, and that would be a type of looking for what we call 2-photon interference. So I'll simply say that we've done some of that, both with the parametric down conversion sources and with the microring resonator sources. You can see a lot of error bars. These are not easy experiments. But here, as we're changing the phase applied to the biphoton, we look at coincidences. There's a clear phase dependence. We can go up to sort of, so far, 3 frequency lines. We'd like to push farther to look for higher dimensions of quantum information. But we can make curves that sort of match what you expect from theory and sort of show this type of entanglement. Okay, some more details I won't get into. And so maybe the last thing I'll say before I conclude is come back to dispersion. So we can tie these together again. And one thing we did that I won't claim it's going to put any conventional instrumentation out of business, but we think it's kind of cute, is to sort of test the effect of dispersion on these effects, or use these kind of quantum optical way to sort of look at the dispersion of a fiber that we insert. So the idea, if we have these various signal and idler lines, and we now put in dispersion, that's a quadratic phase, and that's going to change the relative phase of the entangled photons, even without our putting on external phase with a pulse shaper. So it's going to kind of bias it. And so what we're going to do is, for example, if we look at a particular photon pair, I think number 5 and 6 on both sides, this interference peak was at 0 before, now it's shifted. That's a sign of dispersion. What we can also do is a series of measurements where we pick different signal idler pairs, look at the corresponding sideband, and look at the coincidences of a particular frequency without changing the phase. And we'll see a frequency dependence. And from all these sort of effects, we can pull out the dispersion. And I'll simply say, there's a measure of it, and it's a certain number, which is in 1% of what sort of the vendor, specified number. So at least it kind of tells you understand something about how these states are evolving and how they even interact with the things like dispersion that have been central to this talk. So I'm going to skip one more and limit my overage to kind of the 10% level. But let me, thank you for your attention. I hope what I've done is conveyed the idea that not only can we manipulate with, highly engineerable precision, ultra-fast optical signals, but we can kind of take that capability and do some interesting things actually in broadband RF and other systems, even kind of in the certain types of quantum photonics. And let me simply thank our sponsors and many students who've contributed to various aspects of this over the years. This is a picture of the sort of a most recent, current group at Purdue. Thank you for your attention.